Year 13, Chapter 5, Differentiation, Lesson 3, Connected Rates of Change. So we're going to explore the relationship between the two derivatives, dy by dx, the derivative of y with respect to x, and dx by dy, the derivative of x with respect to y. Now, it helps if we use an example to illustrate this, so that's what I'm going to start off by doing. I am going to choose a very simple function. I'm going to choose y as x squared. So let y equal x squared. Now this then allows me to rearrange this so I can say that x is equal to the square root of y, or x is equal to y to the power of a half, and that will be slightly easier to differentiate. So let's start with dy by dx. Let's differentiate y with respect to x, and of course this gives us 2x, a very simple derivative. What about dx by dy? So dx by dy, remember we're differentiating x with respect to y, so this becomes a half y to the power of negative a half. And I would like to rewrite that, so that is 1 over 2y to the power of a half, which is of course 1 over 2 multiplied by the root of y, which is 1 over, and of course we know that the root of y is the same as x, so this is simply 1 over 2x. So look at the connection here. Can you see it? We can see that dy by dx is equal to 2x, and we can see that dx by dy is equal to 1 over 2x. And this leads us straight into the result, the generalization that we can hopefully see, which is that dy by dx is equal to 1 over, or 1 divided by, dx by dy. And that's a really useful result for us to know, and we'll be making use of that in some of the work that we are now going to do as we look at related rates of change. So please bear this result in mind. Dx by dy is the reciprocal of dy by dx, and vice versa, of course. So you will be making use of that result in future. So we're now going to explore related rates of change, and we will investigate how the chain rule can help us link different types of rates of change. So this is best illustrated with a series of examples. So in my first example, I am going to list some rates of change. dm by dt is going to equal 6, and dt by dx is going to equal 8. Now, I'm not going to give any of these units just at the moment, but that could be something that we will explore a little bit later on. Now, my aim here is to find another rate of change. I would like to find the rate of change of m with respect to x, so dm by dx. Now, I can use the chain rule to do this. dm by dx would be equal to dm by dt multiplied by dt by dx. Think about the chain rule, think about how the chain rule works. We know it's not a matter of the dt parts cancelling out because these are not fractions, these are differentials, these are derivatives, but some people do like to think of it that way. And this is certainly a true statement set up using the chain rule. dm by dx is equal to dm by dt multiplied by dt by dx. So what do we know? Well, we know that dm by dt is equal to 6, and we know that dt by dx is equal to 8. So the answer is dm by dx is equal to 48. So there is an application of related rates of change using the chain rule. So here's a second example for us to look at. dv by dr is equal to 4r, dr by dt is equal to -3, and we have got to find dv by dt. Now I'm going to give this some units. dv by dr is the rate of change of v with respect to r. Now v might stand for volume, so this could be centimetres cubed per centimetre, because r might stand for radius. And then dr by dt, well, that could be a measurement of centimetres per second, for instance. So we're looking for dv by dt, which is the rate of change of v with respect to t. Well, let's apply the chain rule again. So we need to make sure it's v in the numerator, or the upper part, so that's dv by something, so dv by dr. Now, why would I choose that? Well, I have that to hand, so it makes sense to use that. Now, I need to ultimately ensure that I have dt here, so this part has got to be dt, and I don't need the dr, so let's make sure we've got that there, and then, of course, that is here. So dv by dr we know is 4r, and dr by dt we know is -3, so the answer is -12r. But of course, we need the units for dv by dt, and we did say perhaps v could be volume, so that would be centimetres cubed per second, or centimetres cubed seconds to the -1, as you've seen when we've done mechanics. So here's another example. dp by dx is 5x squared, dp by dt is equal to 4, and we need to find dx by dt. So how am I going to do that? Well, I notice the fact that there's an x here, so I need there to be dx by something. And I notice the fact that there is a t here, so I need something by dt. Now, the only other variable that's involved in all of this is p. So if I make this dx by dp and dp by dt, this will then work out. And what I've done is I've made use of the chain rule here again. How have I worked out each part of the chain rule? Well, I've got to look logically. I want to get to dx, which is why I need a dx here. I want to get to dt here, which is why I need there to be a dt here. How did I choose the other letter here, the other variable dp? Well, it's the only other variable involved in the question. Now, dx by dp, well, I don't know what that is, but I do know what dp by dx is. So dx by dp is, of course, 1 over dp by dx. And dp by dt is, of course, just 4. So this is then 1 over 5x squared multiplied by 4. So this is 4 over 5x squared. We don't know what the units are in this example. So let's look at the last example. We have dr by dx and dr by dt, capital R here, and we need to find dx by dt. So same system applies. I want there to be a dx here, so I've got to have this, and I want there to be a dt here, which means I need a derivative with respect to t here. I then look back at the information I've got, and the only other variable involved in this is r, which means this needs to be dr and this needs to be dr. Now, dx by dr is, of course, 1 over dr by dx. That was the first example we looked at. And dr by dt is, of course, equal to 3. So we need the reciprocal of dr by dx, which is -1 over 5 multiplied by 3. So the answer is -3/5. And we found a related rate of change by making use of the chain rule. So let's talk a little bit more about what we mean by a rate of change. I'm going to think of an example here. R is going to be the radius of a spherical balloon measured in centimetres, and t is going to represent time measured in seconds. Now, let's imagine that we know that dr by dt is equal to 5 centimetres per second. What does that mean? Well, it's the rate of change of the radius with respect to time. But what does that mean? Well, it means how much does the radius change by each second. So in this example, I'm saying that dr by dt, the rate of change of the radius with respect to time, is 5 centimetres per second. So what does that tell us? Well, that tells us that as each second passes, the radius increases by 5 centimetres. Now, how do I know it increases by 5 centimetres each second? Well, that's because it's a positive 5. Now, what if we had something different? What if dr by dt was equal to negative 5 centimetres per second? This is still a rate of change, but this time the negative sign tells me that the radius is decreasing by 5 centimetres each second. So what we mean by a rate of change is how much does the first variable change by when the second variable changes by 1 unit. So we're going to explore 4 problems together, all of which involve connected rates of change and the chain rule. So read the information carefully because there is a lot to unpack here. Let's highlight the key pieces of information. A sphere has a volume which is calculated using this formula here. It is being filled with a liquid, so the volume of liquid is increasing at a rate which causes the radius to increase by 5 centimetres seconds to the minus 1. We're then being asked to find the rate of change of volume when r equals 10 centimetres. Now, let's look at the information we've been given, particularly this part that I've underlined in green. Look at the units. They will tell you quite a lot of information. The units are centimetres per second, which tells me that this is dr by dt, centimetres per second. It's the rate of change of the radius, r. So we'll call the radius r. Now, we have been asked to find the rate of change of volume. So we need to find dv by dt. So, what does the chain rule tell us? The chain rule tells us that we can find dv by dt using a connected rate of change. Now, let's think about this carefully. We want there to be a v here, so we need dv. Now, we want there to be t here, so we need part of this to be dt. Now, what's the only other variable involved in any of this? It's r. So what happens if I put dr here and dr here? Well, I certainly know that dr by dt is equal to 5, so I can fill that part in. But what about dv by dr? Do I know what that is? So I first of all got to find dv by dr. But remember, we were given this piece of information over here. We were told that v is equal to 4/3 pi r cubed, so I can differentiate this, dv by dr. Differentiate v with respect to r. So this becomes 4 pi r squared. So I can replace dv by dr with 4 pi r squared. So the answer would be 20 pi r squared. But we were asked to do the calculation when r equals 10 centimetres. So if r equals 10, if we substitute that in, we get this. So the answer in terms of pi is 2000 pi, and we need to check our unit. Well, look at the rate of change. It's the rate of change of volume, v, with respect to time, t. So it's centimetres cubed per second, or centimetres cubed seconds minus 1. So the units can tell you an awful lot. The units can tell you which rate of change you're dealing with, and the rate of change will also tell you the units that you are looking for. So let's have a look at a few further examples. Read the information really carefully before you start the questions. So the driving force F and velocity V are related by the equation F equals 25 over V. And for part 1, we've got to find dF by dV. So F is equal to 25V to the minus 1. Let's rewrite it. So dF by dV is equal to negative 25V to the negative 2. Part 2. Find dF by dt. So we're looking at connected rates of change. So dF by dt, so that means we need a dF and we need dt. And the other variable that's involved in this question is, of course, v. So let's use our chain rule like this. And then what do we know? We know that dF by dV is equal to negative 25v to the negative 2. So that part is fine. And dV by dt, well, we're actually given that in the question. dV by dt is 1.5. So I can very simply substitute that in, 1.5, and this then gives us a formula for dF by dt, which is negative 37.5v to the negative 2, but the question wanted us to substitute in v equals 50. So that's our last job, and let's see what we get. Negative 0.015. Now, what are our units? Well, let's go back to the rate of change here, just to check. So it's dF, which is newtons, by dt, which is seconds. So it's newtons per second, or newton seconds minus 1. Next question. Read the information very carefully, highlight any key pieces of information. So the volume of water in a pond is given by this formula here, and for part 1 we've got to find dV by dH. So look at the formula and you can see it's set up perfectly for us. V is given in terms of H. I would just expand the bracket here, so V equals pi H squared minus 1/3 pi h cubed, and that allows us to then differentiate each term separately. dV by dH is equal to 2 pi h minus pi h squared. Now, part 2. Water is poured into the pond at a rate of 0.02 meters cubed per minute. What information is this? Meters cubed per minute. That's volume per time. So we are being given dV by dt, which is 0.02 meters cubed per minute. So look at how I've used the units here to help me work out which rate of change I have. Now, we are being asked to find dH by dt. So again, I set this up. I need a dH and I need a dt. Now, the other information that we've been given, of course, is dV, or V. We've been given information about the volume. Now, what do I know? Well, dH by dV is, of course, the reciprocal of dV by dH. So this would be 1 over 2 pi h minus pi h squared. And dV by dt is 0.02. So this will give me a formula for dH by dt. But we need to do a bit more than that. We've been asked to find the value of this rate of change, dH by dt, when h is equal to 0.4. So I need to substitute in h equals 0.4. So let's work this out. And this gives me 0.0099471, etc., which we'll round to 0.00995 to 3SF. But what's the unit? Well, it's dH by dt, so h, of course, is the height of water in the bowl or in the pond, so that is centimetres per minute. So the last example that we're going to look at here, water flows into a bowl at a constant rate of 10 centimetres cubed per second. So instantly you should be thinking, what is this information that we have been given here? So centimetres cubed per second, so that's volume, centimetres cubed per time, seconds. So dV by dt is 10 centimetres cubed per second. Now, when the depth of water in the bowl is h centimetres, so we can see that here, the volume of water is V, where V is equal to pi h squared. Find the rate at which the depth is increasing. So that is dH by dt. And we can make use of the chain rule here again. So look how I'm setting it up. I know what I need, the components of my final answer, and I know that this question involves V as another variable. So I know that dV by dt is 10, but I don't know yet what dH by dV is. But I was given this information here, and I can differentiate with respect to h. So dV by dH is 2 pi h, and therefore dH by dV is 1 over 2 pi h. So that's 1 over 2 pi h. And we were asked to calculate this very specifically when the depth is 5 centimetres. So we want to substitute in, and actually this simplifies rather nicely down to give us 1 over pi centimetres per second. How do I know it's centimetres per second? Look at the derivative, it's dH by dt.